You all know that working with a robot with a single external RGB camera is not an easy task. In this talk, I want to present you our system that can use a single RGB camera and allow a robot to grasp objects like this one. My name is Jonathan, and let's get started. We need to find in the camera frame where the object is. We also need to find in the camera frame where the robot is. Once we have these two poses, then we can move back and forth in different coordinate frames. And then we can allow our robot to pick up the object by finding the different transformations that we need. Let's watch a little example of all of the system working together. I start by moving the camera away from the robot. The pose estimation of the robot's happening at the same time as I'm moving the camera, and the pose estimation of the objects is happening at the same time as I'm moving the camera. So everything is calibrated in real time. Let's talk about the different contributions that we're making with this work. We're presenting a system that allows a user to move freely around a robot, take the camera, move the camera. Online calibration is happening in real time. We also achieve approximately 2 centimeters accuracy on the different poses of the objects. This allows a robot like Baxter to be able to pick up the different objects. And then we're also introducing 28 toy objects with 3D models and pose detectors for all of these objects to expand availability of computer vision research to roboticists. Cameras are used differently in different robotics systems. For example, we can use a depth camera that provides with a point cloud, or the camera could be mounted directly onto a robot arm, which allows a robot to have a single calibration, and then afterwards the arm can move freely in the space. Also, we could use reinforcement learning to learn policies that are conditioned on the position of the camera. So if the camera moves, then the policy has to be relearned in order to know what's going on. Here's an overview of our system. We have an image coming into the system where we can see an object and we can see the robot. The same image is going to be sent to two branches. The first branch at the top is the Dream branch. Dream is our system that we presented recently to do robot pose estimation. At the bottom, we're going to send the image to our pose estimator, or deep object pose estimation, DOPE for short. The DOPE pose estimator is going to find the pose of the object. Then we're going to take that pose and use another algorithm called SIMTRACK to refine that pose, and then both of the poses found for the robot and the object are going to be refined using a moving average. And in the end, once we have all of that information, we can move from the pose of the object all the way to the coordinate frame of the robot. Deep pose estimation works as follows. First, we find key points that form a cuboid around the object. Then, because we know the object already, we know the size of it, right, we have the dimensions. Using an algorithm called PNP, we can reproject the 2D key points into 3D. Once we have that, we have the pose of the object. All of these pose detectors were trained on synthetic data, so data generated by a computer. The output generated by DOPE is then sent to a refinement step. We use the framework called SIMTRACK. SIMTRACK uses swift key points on a texture objects to be able to refine a pose. So given a pose and then a set of swift key points, the algorithm refines the pose and kind of track what it sees in the image. In order to find the pose of the robot, we're going to use a framework very similar to what we use for DOPE. We're going to define key points on the actual robot that are predefined, and we know where they are with respect to the base. And then we're going to train a neural network to detect these key points. Using PNP, because we know the size of the robot, we're going to be able to find the actual 3D pose of the origin of the robot. With all that information, then we can find the actual pose of this whole robot when we look at it. All the different poses that we found so far through Dream, DOPE, SIMTRACK are going to be sent to a pose filtering. Because some of these pose estimators might have false positives, there might be some errors. So what we want to make sure is through time that things are smooth. So we're just going to use a weighted moving average And that way the moving average is going to allow us to, I don't know, hide the camera, for example, for half a second, and poses are going to stay stable. This allows our robot to be able to move in closed loop fashion and track an object, for example, with its gripper above an object. Let's look at more examples of the robot picking these new objects. So each of these videos start with me moving the camera, so sort of showing that the camera can do the pose estimation, online calibration, and then as we move the camera, the rest of the system will find the pose estimation of the objects, and we'll have Baxter afterwards go in and grab the object. As you might have noticed, we're introducing these new objects, 28 of them. These are toy objects that you can find quite easily online. There's some links for buying them through online stores in the paper. And we have 3D models for these objects and pose estimator as well for these objects. So you can go on to the GitHub page for DOPE. There's a link here, and you can download the different weights and being able to detect and do pose estimation of these objects for your own research. We did 2 different experiments, a positioning accuracy experiment where we had a closed loop tracking Baxter or robot on top above the object, and another one where we freely moved the camera and we did some analysis over some of the errors that we can observe. The setup that we had was a Baxter robot from Rethink, a single GPU at Titan XP, and a single RGB camera, the Logitech C920. For the positioning accuracy test, what we did is we had the robot in a closed loop servoing above the object, like this. We attached some weights at the middle of the gripper of the robot, right? So the weights are on this like kind of pendulum. So as the robot moves, it stabilizes above the object with our system as we move the camera around, as we move the object around. Then once the system is stable, we take a ruler and we measure from the center of the object through where the pendulum is, where the weights are. This gives us sort of an accuracy for a top grasp. So for this experiment, we use 5 YCB objects. For these 5 YCB objects, we recorded 7 different locations on the camera. So the distance from the robot base to the camera, which went from about 1 meter to 1 meter and 60 centimeters. And the camera could see the torso of the robot and as well of the object. Right. And as you can see in this graph, the lower it is, the better it is. So the lower the accuracy that we're reading, the better the graph is going to be. The tolerance for Baxter is about 2 centimeters, and we can see that we're achieving most of the time for most of the objects that below that 2 centimeters. Where we observe some errors with the mustard, shown here in orange. Because the mustard doesn't have much texture, when we run SIMTRACK on the actual mustard, we saw some problems and discrepancies in terms of the pose estimation. And there might be some other problems because of labeling that might have changed between the one we used, the 3D model we used versus the actual model that we had. We ran a similar experiment for the 28 objects that we have. We can observe here that the spaghetti, this box, was quite challenging for the pose detector because it is super long. Our pose detector was having a hard time finding the actual corners correctly, which lead to quite not so good results. It's very highly encouraging for the research community that is looking at pose estimator. Solving these problems are going to be very interesting for roboticists. The second experiment that we ran was doing an analysis of how moving the camera would affect the end effector position. So we took the camera and moved it around about 1 meter in depth, and then a little bit 30 centimeters back and forth to the left, to the right, and up and down. So we recorded this motion while the robot was servoing over an object. So the robot is using all the different poses are coming out of the camera in order to servo above that object. As we're moving the camera around, we're observing some noise and some errors, as you can see in this graph. So if we had a very perfect system, all these three lines that you see will be completely flat at 0. What we're observing is some compounding errors. So it starts at 0, and then as we move the camera, we have different axes going in different directions. So for example, the red axis is moving forward or backwards. That's the X being in red. The green axis, which is the Y, is moving left and right. And then the blue axis, which is the Z, is moving up and down. And you can see that everything is kind of moving a little bit within 2 centimeters, which is still within the reach for us to do a grasping. But again, here there's some performance increases that we could get. In conclusion, we presented a system that allows us to do object pose estimation at the same time as robot pose estimation, which provide us with an online calibration that is precise enough, approximately 2 centimeters, to do robot servoing above an object, for example. We also introduce new objects for researchers to do pose estimation work on, and as well for roboticists to use and to do grasping experiments and have different interactions as well between the objects. Thank you for watching. I hope you appreciate this work, and hopefully you'll be able to build on top of it. Thank you so much.